So first, how I did the data cleaning was I added the CSV reader, and then here I added the chosen file, and next I added the rule engine as I viewed the data from the statistics view node. I can see that one of the data was actually put as the numerical data type, and I decided to change that as it's easier to interpret and to understand. So by doing that, I added the rule engine node. So what I did was I put this code in, I wrote this code, and so initially it used to be 1, 2, 3. So 1 will now be never smoke, and 2 will be this, and 3 will be this. And then I put the name as smoking status. So there's a new column, as you can see here. So this is the new column here. And as you can see, there's no missing values now. Initially there was, so I added the missing value node, and I put it as remove row for all of it to remove the missing values row. And then I added the CSV writer so I can export the clean data set. Also, I can view the statistics node for numerical, variable, and categorical by choosing here. But now I included everything, but actually you can like exclude, and you can also see like what kind of statistics do you want to view, which is all in here, and you can include it here. And now we're going to view the report 1. So for report 1, this is the report 1. So first for histogram, box plot, I want to look at the triglycerides and serum creatine. So I just put it under a row, and then I make sure that I take off aggregate measures. And so this is the box plot, as well as for the triglyceride, which is here. And I can also view the outliers for this. So this gives me more information. And then for the histogram, I put it as the age. I put the data over here, and then I put the count as the row, so it shows me the count for the age. So it's all in here. As well as for total cholesterol, it's the same thing also. And for the smoking status. So this gives me information on how many smokers there are, and non-smokers, and people that used to smoke. And for the pie chart to view for drinkers and non-drinkers, this is to put for the color, and then I put the count, and then I put the label. So I just view it here, so I can see that there's more non-drinkers than drinkers. And I did the same thing for the gender, so there's more male than female. To view the linear correlation table, you're going to go to NIME instead. So you can view it by the linear correlation node. So for now, I only put SBB and the others. But if you want to see everything, you can actually include it here. So this is how you can view for all of the different types of data. So using this, you can see which data are like positively correlated or negatively correlated. So how I did the bar chart to view the different liver enzymes and their relationship. So I put the column as for the drink, yes or no, the drinkers and non-drinkers at the column, and then I put the 2 different liver enzymes at the rows, so it shows me 2 here, and then I put the label for the count, so then I can see the difference over here. So from here I can see that the alcohol drinkers have higher levels of liver enzymes compared to non-drinkers, so it can help me compare between the two. So I did the same thing for this, but here I added the gender, so now I can see whether they are drinkers and also whether they are male or female. So for my report 2, my first question, which age group shows the highest levels of cholesterol among drinkers? So this is only for drinkers, so I had to put a filter here for only drinkers, which is the Y, which means yes. So I added the column for the age groups over here, and for the rows I added the total cholesterol and I put it as the average. So it's easier to interpret the data instead of the total, like the count. So then I put the color and I labeled it, and I made sure both of them were average as well. So from here I can also conclude that the drinkers age of 40 to 49 has the highest total cholesterol here, and then the lowest is the age group 20 to 29. So from this I can conclude which age group has higher chance of risk, like cardiovascular risk, and also can highlight a potential trend where drinking might contribute to higher cholesterol levels at age group 40 to 49. For the same question, I also did a box plot. So this shows me the spread for the age groups and then their total cholesterol. So from here I can see that the age group over 50 has like the wider spread of cholesterol value, which means they have a wider range in compared to others. And also I can see like outliers, which shows me that some individuals from this age group has like exceptionally high cholesterols. I can also see from here that this age group 20 to 29 are in lower risk. So for this question, the drinking status correlate with liver enzymes. So I have both liver enzymes here. So I put one at column, put one at row, and this is for non-drinkers. So I have to put the filter here as no, and then I also put the color on it, and then this is for the drinkers, and then you can see I put it for yes. So I can see that both of them they show positive linear correlation between the two variables, and that both liver enzymes increase together. And from this I also can see the R value for both scatter plots. So it indicates it shows a moderate correlation. So for the drinkers, it shows that it's steeper and more clustered over here. So it suggests like higher levels of liver enzymes as compared to non-drinkers. The non-drinkers is more spread out compared to this. So this scatter plot really shows me their relation to each other. So I can conclude that the liver enzymes for drinkers are higher, so they are more in risk for health problems such as liver damage. Before continuing with my further investigative questions over here, I'm going to explain how I did my data transformation. So how I did the data transformation, I did it on Tableau. So first you can go to analysis, and then you can go to create calculated field, and then you can write it here for the label and then the calculation here. So let me go through with you the ones that I've already did. So I did it for age group, so the data will be easier to understand. So then I did this code here. I'm familiar with this since I learned this for Python. So as you can see here, this means that if the age, which is the data here, is under 20, then it will show as under 20. So the same goes for all of them, and the end means we have come to the end of the code. So therefore, I'm able to put my data in different age groups like this instead of it being all spread out and being messier. So then I did this formula for the BMI. So I put the weight from this data over here and then the height from the data over here. So we can calculate the BMI for me. So then I did the same thing as the age groups for the BMI categories, which is over here, which is the same thing as if the BMI field is under 18.5, then it will be shown as underweight. And the same for everything else except else obese. So for my third question, is there a difference in average blood sugar levels between drinkers and non-drinkers? So I put the drinking data over here, the non-drinkers and drinkers, and then I put the blood sugar levels and I put it as the average, and then same for the label, I put it as average, and then I put the color for drinkers and non-drinkers. So from here I can conclude that drinkers have a higher average blood sugar level, which shows that alcohol may affect people's blood sugars level. So for my question 4, I wanted to see whether drinking alcohol consumption can influence metabolic parameters. So from the data transformation I did for the BMI calculation, I put it in the row and I put as the average, and then I put the drinkers and non-drinkers over here at the column, and then I colored the BMI and put an average and also as a label as average. So from here I'm able to conclude that drinkers have higher BMI than non-drinkers, so it may suggest like weight-related issues for drinkers, as alcohol can contribute to high calories. So I also did a pie chart, so it's also like easier to see. So I did one for drinkers, and I put over here the filter for yes, and then I put the color and I put the average for the labels, and so this is how it looks like. So I'm able to see here. I did the same thing for the non-drinkers. So this is non-drinkers and the drinkers, so I can compare the difference between the two. So after comparing the two, it shows me that there's a higher BMI for people who are obese, as well as a larger proportion compared to non-drinkers. So higher BMI, so it shows that drinking may influence higher BMI, and it can impose higher risk onto those people. So for my next question, I want to see how does systolic and diastolic blood pressure change based on smoking and drinking status. So first I put smoking and drinking over here on column, so I'm able to see here and below here as well. And then I also want to see systolic and diastolic, so I put the average over here and I put it in the rows, and then I also wanted to color it, so I put the drinking status into a color here. So this for all, and then each systolic and diastolic I put the label over here. So from this I can see that individuals who smoke has the highest average systolic and diastolic blood pressure across the drinking categories, and the drinkers also have higher systolic and diastolic blood pressure compared to the non-drinkers. So smoking has a significant impact on the blood pressure, and drinking has a moderate impact. So for question 6, I'm able to look at it on 9. So I can see the linear correlation over here. So you can see that systolic and diastolic they are strongly correlated, and also strong positively correlated, as shown by their deep blue color, and I also can look at their values. So it says over here. So also by the comparison of the values, it shows me that the relationship between systolic and diastolic blood pressure is stronger than the HDL and LDL cholesterol. And I also chose those data by including it here in the linear correlation note. So for my final question, I want to see how does alcohol consumption and smoking status impact triglyceride levels across different age groups. So first I put the smoking status and the age group on the columns, like here. and then I put the average triglycerides, and this is for non-drinkers, so I put it as no, and I also colored it and put the labels on it. So these are non-drinkers and drinkers. So from here I can conclude that drinkers have higher triglyceride levels compared to non-drinkers. So it suggests that alcohol can affect the levels, and that smoking can also affect the triglyceride levels. As previous smokers that have already quit, their levels are lower compared to current smokers, suggesting that quitting smoking can lower triglyceride levels. So it also shows that triglyceride levels tend to increase with age, but then it's generally lower when it comes to age group over 50. So for my logistic regression, I added the CSV reader and I imported my clean data. So then I added the partitioning node initially before adding a normalizer at first. Then I changed it to 70 for the relative, and then I made sure that this was drinking status. As the drinking status is my target variable, so this whole thing is to help me predict being a drinker based on the chosen variables. So in the logistic regression learner, I chose my variables over here, so this is what I included and this is the ones I excluded. And I made sure that the target is drinking status. And then I added the logistic regression predictor, which instigates the predictions, and next I added the scorer. So this is which provides insight into how accurately the drinking status is predicted. So I made sure that this was selected. But after that, I came into a problem initially that this had a problem, and so I added a normalizer to adjust my epochs. So this was the problem that I encountered, so I had to set my epochs limit higher, which I did. So in the logistic regression learner over here, I put the epochs as 50,000, so I increased it. So after that, the error was gone and I was able to. So before, this was my accuracy, and this is after. So the accuracy showed improvement. So the normalizer, in conclusion, the normalizer helped to normalize the data, as previously it might have been improperly normalized. And increasing the epochs level helped me to improve the machine learning by allowing it to keep going over it, which improves the accuracy.